Hello, everyone. Thank you for joining me for my second lecture. In case you weren't at my first, my name is Nathan Ernest Noble. I'm a quantum computing application researcher at IBM Quantum. And in today's lecture, or in this lecture, I'll be speaking about pulse-efficient quantum circuits. The real idea that I hope to reveal through this lecture is showing how you can leverage the low-level control of our quantum hardware to improve the results when you're running on it. So let's go ahead and jump in and discuss the overview. So for this talk, there's three main sections that I'll be focusing on. The first is talking about calibration of single and two qubit gates. Namely, you have this quantum circuit elements, whether it's the X gate or the C naught, and a variety of other things. And I want to sort of help reveal how it is that you get those different sorts of gates at the quantum circuit when actually considering the underlying controls that you have to use on the hardware. Then I'm going to move into this idea of circuit transpilation. So this is the process in which you take some idealized quantum circuit and actually map it to a real backend of some sort with a given connectivity as well as other potential limitations and ways that you can sort of help improve the results when you're doing that. Specifically, I'm going to try and take this sort of pulse perspective versus a gate perspective and demonstrate how differences can arise at times. Lastly, I'll finish off with discussing this idea of continuous gate sets, namely a way in which you can take that cross-resonance interaction, which is what we use for a two-qubit gate, and scale it in a careful manner such that you can get a continuous set of gates from that cross-resonance pulse and actually help it have a more efficient implementation for certain sort of gates for a quantum circuit, with the hopes of revealing how this is specifically useful for quantum machine learning. So with that said, let's go ahead and jump in. So the basics behind calibration of a single two-qubit gate, we can start off with this sort of picture on the right, in which we're going to have two tones. One tone is going to be probing at the frequency of our qubit, and the other is probing at the frequency of our resonator. The very initial calibration that you have to do is actually to find what the frequencies are here. So in that sense, you'll end up doing two-tone spectroscopy, where what you'll do is you'll sweep this F01 and then afterwards sort of measure the state of the resonator. At some point when you actually get onto resonance with your qubit, you'll see that your resonator now begins to shift its state. And from this, you now get a rough calibration of your qubit frequency. And there are some ways in which you can do fine calibrations for this as well. But now, once you've taken sort of these generic pulses and found the excitation of your qubit, you want to now start to think, how is it that we can actually get this X gate, say, for a single qubit gate? So to that end, we're going to take these pulses. They'll start off just having a generic shape with some duration t and an amplitude as well. Now, in order to actually get the X gate, you're going to have the qubits start off in the ground state. For the sake of simplicity, let's keep this duration t fixed. When we keep that fixed and then slowly increase the amplitude, what you'll find is that your qubit starts off in the ground state, but begins to rotate about the Bloch sphere until eventually it gets into the one state. Now, if you were to continue increasing your amplitude, what you would end up finding is that you get these oscillations where it starts off at some point, comes to another maximal point here, and then as you continue to increase your amplitude, it oscillates back and forth. These oscillations are known as Rabi oscillations. And it's from these oscillations that you can calibrate your X gate. Namely, pi pulse from your Rabi oscillation is going to give you the rough calibration for your X gate. Pi pulse just simply corresponds to the angle of rotation about your Bloch sphere here. Now, this is going to be the sort of initial rough calibration. There are some details as to how you can fine-tune the amplitude, which we'll get into in a second. But before doing that, I just want to discuss this idea of the pulse shapes itself. So, namely, you can take these waveforms that you're sending at the qubit frequency and have them have a variety of characteristic shapes. As shown here, we have two different ones. So we have the control pulse for our qubit. This happens to be on qubit 4 for some device. Is represented by D4. And this is actually going to be what's known as a drag pulse. So I'll discuss what that actually is in a second. But it's some sort of Gaussian type shape pulse. And then down here you have what's known as sort of a Gaussian square pulse, which we use for our qubits. Now, one important consideration. So earlier I said, let's keep that T fixed at some arbitrary value and increase the amplitude. Well, one thing that you often end up wanting to do when trying to think about quantum control is you want to make these gates as short as possible. For single qubit gates, important consideration that you have to take into account is that as you begin to shorten the duration of your 0-1 excitation, at some point your pulse will be so short that you can actually start to excite higher energy levels. And these are sort of known as leakage errors. So you are in your computational space of 0 and 1, and you begin to leak outside of it into the 2 state, or if you're doing particularly bad, say even higher than that. So in order to overcome these sorts of errors, this is where this idea of a drag pulse comes from. So drag stands for derivative removal by adiabatic gate here. What this is basically saying is that you have some Gaussian pulse, and you're going to, on top of this Gaussian pulse, add in a component that is proportional to the derivative of that Gaussian, namely this derivative, the d in the drag here. So now it is with this that you can actually suppress leakage errors into your 2 state. What's nice about this sort of drag pulse here is that it has a very nice analytical form, which is discussed in good depth in these 2 papers here. I will say now that this is an active area of research in which people try to construct pulses that maybe are sort of beyond drag in some sense, to get the fastest possible gate that you possibly can get while having no leakage errors as well. And some of these things say we'll use classical machine learning is a way in order to achieve those faster pulses. When doing so, they often end up requiring sophisticated measurement techniques and whatnot. And if interested, please follow up with me, and I'm happy to sort of point you in the direction of some recent papers that do these sorts of tasks of shortening that pulse to a large degree. Just to give you a sense of timescale, our backends, typically for single qubit gates, use pulses that are on the duration of, say, 35 nanoseconds, roughly. For single qubit gates that sort of go beyond this drag pulse type implementation, the fastest I've seen is something that's, say, on the order of 5 nanoseconds. And this is from some of our researchers out in Zurich, actually. So I'd be happy to point you to those papers if you follow up with me afterwards. But now, earlier I mentioned this idea that this Rabi oscillation is a rough calibration. What is it that I mean when I say rough calibration? Well, what this means is that I've calibrated the amplitude that will get me to rotate from 0 to 1. But most likely it's going to actually be off by some amount. So to help reveal this, what we're going to do is, for the sake of argument, move to this sort of pi/2 regime. To do that, we're just going to say that there's a linear scaling here. So in order to get from pi to pi/2, I'm just going to take the amplitude that I had at pi and cut it in half. This will be okay because we're still going to do some calibrations on top of this to help improve things. Namely, so Zlatko earlier in one of his talks had mentioned this idea of coherent errors. So in our pi/2 pulse here, if we assume that there's some sort of coherent error, we can measure it, say, by being off by some amount epsilon. And just so you know, I'm pulling these figures from the paper that's referenced on the bottom. So please do check it out if you want to see some of the details that I don't necessarily discuss in this talk. But we are going to be off by some amount epsilon. Now, that amount epsilon is going to be so small that maybe we can't actually sort of resolve it with just using a Rabi oscillation. So what we can do is this sort of iterative amplification. So we're going to take the pulse and, say, apply it 3 times. And when we do so, we're going to get some error of 3 epsilon. And then if we did it again, we'd get sort of 2 more times, we'd have 5 epsilon. Now, if you repeat this process, what you'll end up finding is that you started off on the equator, and then as you were sort of pulsing the sets of 2 sort of pi/2 pulses repetitively, you'll end up seeing that eventually you're going to amplify the error, and you get this sort of what we call a ping pong pattern, where you bounce back and forth on this thing. It is through this that you can now begin to do fine calibration of your qubit or of your pulse amplitude. Namely, you can begin to adjust your amplitude until you sort of minimize how much you're deviating off of this. And this is the way in which you can then get a fine calibration, say, for your single qubit gates. Now, this is one gate that you need in order to have sort of universal quantum computation. So we've discussed, say, the X gate or the root X gate. And now we still need a few more gates in order to get to this universal gate set. One that will begin to get us there is the Z gate. So a phrase that I love to use from my colleague Nick Braun is the only perfect gate that you have is the one that you don't do, which is the idea behind our Z gate here. So namely, we use what's known as a virtual Z gate. What this really ends up meaning is that you don't actually have to send any pulses into the fridge or to interact with your qubit in order to do any Z-type rotations. Instead, what you can leverage is the fact that when you go from the lab frame of reference to the from the qubit frame of reference to the lab frame of reference, you're going to see that your qubit's sort of processing about the Z-axis. From this fact, you can then actually use the phase of your classical control electronics to implement rotations. So the Z gate now is just implemented by adjusting the phase of subsequent pulses in your control electronics. And it's about in this way that we can go from rotating about the x-axis to rotating about the y-axis as dictated by this unitary here. So if we have a phase that's 0, then we'd be rotating about the x-axis. And if we have some phase that's, say, pi over 2, then we'll be rotating about the y-axis. And this is now how we can, through the combination of these two pulses of the X gate and this virtual Z gate, or more so the root X gate, we now can have universal gate sets for single qubit gates. We're not fully there in the sense that we still need to be able to do 2 qubit gates, which I'll discuss in just a moment. But one thing I wanted to point out is that this also now is a way in which you can begin to think about doing. Sorry, I realize actually I want to go back here and just quickly mention what I've shown here is a plot in which we have a pi over 2 pulse with some delay and another pi over 2 pulse. This harkens back to that Ramsey oscillation that I discussed in the previous lecture. This here is actually a way in which you can now use the Ramsey oscillation to get a fine calibration of your qubit frequency. So earlier I discussed this idea of scanning the frequency and you see some point when you've excited your qubit. That's the rough calibration for your qubit frequency. You can use this Ramsey oscillation actually as a way to get fine calibrations. One thing I'll definitely point you to is the Qiskit textbook in which some of these details are actually covered. But going back to this, one important thing that I want to mention is this idea of dynamical decoupling. So namely, you can improve the coherence of your qubits through adding in this sense of dynamical decoupling. Namely here, so we have the same Ramsey experiment, but in the middle, what we're actually going to do is add in an extra pi pulse. What this will end up doing is it helps improve, this is sort of known as a T2 echo. And the T2 echo is slightly different than the T2 I had mentioned in the previous lecture, but it helps, it tends to be a bit better than the T2 star, namely coming from this fact that you can treat the qubit as being sort of a collection of spins in some analogous sense that are inside some magnetic field. That magnetic field will be non-uniform. And so those spins will start to precess at different rates due to the non-uniform nature of the magnetic field. Now, as they're precessing at different rates, if they're, say, on the equator of the block sphere, you'll see that they begin to spread out. By adding in this pi pulse, they'll begin to sort of precess back the other way. So if you take the pulses or the arrows here and flip them to the other side of the equator, they then begin to precess back together. So it's in this way that your state will then end up sort of being better defined, and so where these arrows are pointing will be better known in some sense. This idea of dynamical decoupling will also be important in trying to think about how you can actually improve the 2-qubit gate with our backends, or namely this idea of echoes. So we'll get into this sense of an echoed cross resonance. So jumping in now, we've discussed our single qubit gates and how you can get your X gate, your root X, or the Z gate. Now we actually want to understand how is that we get the 2-qubit gate, namely the CNOT. So here I've just drawn what you've likely seen of this Bell state. So I do some Hadamard, which is built through that root X gate with some phase shift, and then a CX which now I'm going to explain how it's built out from the cross-resonance gate. So the cross-resonance gate, the way that it works is we have two qubits, Q0 and Q1. In our case, we're going to be using fixed frequency qubits so that they can have those better T1 and T2 properties. And in this case, they're going to be coupled by some linear resonator. Now, the cross-resonance gate, the way that it works is that you take one qubit, say Q0, and you drive it at the frequency of qubit 1. What this ends up doing is this imparts a rotation on qubit 1 dependent on the state of Q0. Putting this into sort of more of a mathematical framework, the interaction that this leads to is this right here. And there's actually some terms that are not necessarily included on the slide right now. Of these terms, the important one to consider is this ZX interaction. So this ZX interaction is the thing that will actually allow you to build a CNOT. And we're going to walk through how that actually works. But something that will, after we walk through building a CNOT from the ZX interaction alone, I want to then highlight how these other terms can be removed. So ideally, you would only have this interaction here, but there do exist some other terms. And so we have to come up with ways to remove them such that we get this clean, high fidelity CNOT that we ideally would like to have. So to this end, if you take that ZX interaction, so namely if you just take a tensor product between your two Pauli matrices of the Z Pauli matrix and the X Pauli matrix, and then you exponentiate that, what you can end up getting is a matrix like this. Where this angle of theta is going to correspond to how long of a cross-resonant pulse you're using, or to what the amplitude of this pulse is. Basically, this theta will be the area under the curve of the pulse that you are imparting. So now, for the sake of simplicity, or for the sake of argument, let's take this angle of pi over 2, and then now we get this matrix here. We can see that this still is not the CNOT that we want. So then we're slowly starting to realize that in order to build a CNOT from our cross-resonance interaction, we need more than just the cross-resonance. What that comes down to is you have this ZX of pi over 2, but then you're also going to do a rotation of, do two more gates that correspond to ZI and an IX rotation. However, we haven't really covered how you can isolate that ZX interaction term alone. So to that end, let's go ahead and review how we can actually take the true interaction that you have for your cross-resonance gate and use some clever tricks to remove undesired interactions. So when you have the cross-resonant tone on, it leads to this Hamiltonian interaction terms that you see on the right, highlighted in purple. The cross-resonant tone is shown here in the left-handed side, where we have this, what's known as a pulse schedule, which is actually just revealing the sort of pulse waveforms that you use when actually controlling the hardware. So namely right here, we have selected this sort of orange or yellow tone. This is actually the cross-resonant tone that gives rise to these interactions, as well as some others. So this is great, as we've said, because it gives us this ZX term that we actually want, but now we want to start figuring out how we get rid of some of these others. So to start, what we end up looking at is this essence of an echoed cross-resonance. So the echoed cross-resonant consists of both of these tones here, both of the sort of your orange cross-resonant tones, as well as these two pi pulses here. So what the pi pulses end up doing is in essence equivalent to that dynamical decoupling that we had earlier, where you can flip the state of your qubit, and then it can begin to process in some opposite direction such that you can actually remove certain terms that you don't necessarily want to have. So what this basically is you apply some pulse before, you evolve your cross-resonance gate, or you apply your first cross-resonance tone, you apply another pi pulse, and then you evolve this cross-resonant tone in the opposite direction. If you were to sort of take this is now say a ZX pi over 4 and another ZX pi over 4 tone, times these two X gates, and you look at the sort of associated unitaries, you can see that this leads to the ideal ZX interaction that you'd have, or a better way to put it is that these two pi pulses aren't going to change the desired ZX interaction, but at the physics level, sort of the physical interaction levels, you're actually going to cancel out this ZI and this IX interaction term. So this is great in that we've now removed some of the terms that we don't want to have. However, there exist some other ones that I haven't drawn or put into this Hamiltonian out of the sake of simplicity. But you might take a look and see that there exist these other tones right up here on your target qubit. So these are what are known as rotary terms. These rotary terms help remove different interactions that I didn't highlight before, namely say this ZY type interaction or a ZZ type interaction. So it is now with these this echoed cross resonance tone and with some rotary terms that we've now isolated that ZX interaction. And at this point, we just have to do what we mentioned a second ago, which is apply some rotation on your target qubit, and then also apply some Z rotation on your control. And the Z rotation on your control qubit will actually end up imparting some phase on your target qubit if you don't necessarily get it correct. So this now is where we have our C0 gate that we wish to have, built from an echoed cross resonance with rotary tones. I want to say here that this isn't actually the most up-to-date 2-qubit gate based on a cross-resonant interaction. Namely, recently IBM published some work in which you can do what's called a direct CX gate. So the direct CX gate actually uses some improved control techniques within the cross-resonance tone, such that you don't need to have these echoed terms, while you can still remove the ZI or the IX type interactions. When you get rid of these echoed terms, then what you end up doing is shortening the total duration of your C0 gates. And in this way, you can get an improved sort of performance in your quantum circuit. And it was this actually that we used to improve the quantum volume of one of our circuits a while back. And it's in this flavor that you can do a lot of really interesting research within this space. I won't touch on it too much, but another very recent publication coming from IBM Japan was some work with a cross-cross resonance gate. So rather than having driving one qubit at the frequency of the other, you drive both qubits at the frequency of the other. And then in this way, you can actually implement sort of a native swap gate in our hardware, which ends up being much more efficient than if you tried to do it with the C-naughts alone. So this now covers all the details in terms of getting this cross-resonance gate to be the ideal C-naught that you want. To that end, I now want to get into this idea of circuit transpilation. So let's go ahead and jump in. In case you're unfamiliar with this, the idea of transpilation is that you have some idealized quantum circuit in which you want C-naughts between various sets of qubits. You may be familiar with this circuit here. But you say want to do a C-naught between Q4 and Q0, or Q4 and Q1. But then when you actually take the real quantum hardware that you want to use and you look at it, what you'll end up seeing is, say, that Q4 in the instance of this specific chip doesn't actually have any connection with Q0, or also it doesn't have any connection with Q1. So because of this, you're going to have to introduce swap gates and whatnot in order to actually get this circuit to be able to run on some real quantum hardware. When you do this, you can do it sort of well, in which you ensure that you get the minimum set of gates that you possibly need to implement this circuit, or you can do it in sort of a poor manner. And when you do it poorly, what you'll end up finding is that you say get a lot of C-naughts, and then now the importance of this is that if you do it well, all real quantum hardware is going to have noise. But if you minimize and minimize, say, the number of C-naughts and transpile this circuit well, then what you'll see is that your correct answer is able to stand out above the noise. But if you do it poorly, then all of a sudden the answer that you actually are trying to get from your quantum hardware is going to be buried in the noise. So this is a very important consideration that you have to think about how to map this well. Now, within Qiskit, there's this transpile function in which you can take this idealized quantum circuit and whatever backend you're interested in, and then map that to the hardware using different optimization levels. So zero, say, is really not doing any sort of optimization at all, only taking into account the connectivity of the device and then mapping it sort of accordingly. And then as you increase, you can begin to do higher levels of optimization in which you say collapse redundant gates or find sophisticated ways of reducing the number of CNOTs. This is an active area of research as well, in which there's a lot of different techniques that you can try and use to get the best results possible when doing transpilation. So one idea, say, is to do this noise-aware transpilation, where you can actually take into account the various properties of your backend, so the T1s or T2s of your qubits, or the fidelity of different gates, and then see how those noise properties will impact some result and try and route what qubits you use sort of in an intelligent manner. Now, this is all of this discussion that I've had thus far is transpilation when thinking about it at the gate level. So what I now want to get into a bit is how you can think about pulse level transpilation and how that actually can help lead to different benefits in terms of reducing the duration of your quantum circuit. So how long it actually takes to run all the variety of gates or to run the circuit itself. To that end, I think a nice straightforward example of how a gate pace perspective will differ from a pulse based perspective is this idea of an open CNOT. So namely, if you have a CNOT which is controlled on the 1 state, if you wanted to instead make it controlled on the 0 state, you add an X gate before and after. If you just look at the straightforward way in which this ends up getting mapped to a backend, it looks something like this, where now you can see that you have a series of single qubit gates that exist around your cross resonance. So this part in the center here is the CNOT that we discussed that's built from the echoed cross resonance that we discussed. But then now here are the 2 X gates before and after. One thing that you could immediately do to make things a bit better is fold in these pulses inside such that you end up not necessarily wasting that extra time. However, another thing that you can actually do is build the 0 controlled CNOT directly from the cross-resonance interaction. So namely, you can take this pulse here, flip it in the opposite direction, and then now all of a sudden you've built this open CNOT. So writing it down in the mathematical formalism, earlier we had this UZX of pi over 2 with ZI of negative pi over 2, and before it was IX with negative pi over 2. In this case, we're going to do a positive pi over 2, and this actually ends up giving you an open controlled knot up to some global phase. So this is great. We've now shown taking a pulse-based perspective can help reveal that there are ways in which you can reduce the total duration of some circuit, even say in the instance of an open CNOT. Now, another thing that I just generally want to make you aware of is that when you are operating at the circuit level and you think about reversing the direction of your CNOT, you might naively think that what you're actually going to do is switch the underlying interaction. So namely, if I wanted Q1 to be my control qubit, I'll drive Q1 at the frequency of Q0. And if I wanted to flip it and have Q0 be the control qubit, I'll drive Q0 at the frequency of Q1. Well, this isn't actually what happens in the back end, and that's what's shown here at the bottom. Instead, what you're going to do is reverse the direction of your CNOT by applying Hadamard's both on your target and your control before and after the gate. This is sort of a Hadamard reversal. It's an identity that exists, say, at the quantum circuit level. And you can see the implementation here where now on this reverse direction, you have some extra gates both on your target and your control. So this is nice actually because one, the cross-resonance gate is not necessarily symmetric. So driving it in the opposite direction, one direction will end up being a bit slower when you try to calibrate it up. But another important aspect to this is that it actually reduces the number of calibrations that you need to do, which is really good if you're trying to sort of think about making you don't want to have to run calibrations all day and then never actually be able to run quantum circuits. So you want to run sort of a minimum set of calibrations that end up giving you a good stable system, which applying this Hadamard reversal trick is a good way to doing this. Now, I've discussed some sort of underlying details of how this pulse perspective can change or help you understand what's actually going on when you do things at the circuit level. One thing I now want to bring up is this specific gate of a controlled RZ set. When you take this gate and you map it to a backend, using the sort of native gate set that generally exists, namely these C0s with the various qubit gates, it'll sort of get mapped to something like this, where you have two C0s built from those cross-resonance interactions, as well as some U1 gates or RZ rotations. So if we're going to pick, just for the sake of argument, a very specific angle of pi. So when you pick this angle of pi, what this ends up corresponding to is something like this, where you have a U1 of pi over 2, a C0, U1 of negative pi over 2, and another C0. If we go back to this idea of the optimization level and set it equal to 0, then it will transpile in this way and not try to do any sort of optimization. And then if you look at what this ends up appearing like in a pulse schedule, you can see this, where you can see that there's one C0 here with some U1s, U1s at the beginning as well, and then another C0 built from that cross-resonance gate. Now, if we were to take this optimization level for this specific angle of pi and crank it up to 3, so try and just do the most optimization to make this as efficient as possible, the Qiskit transpiler can be aware of the fact that, in fact, for this specific angle of pi, you don't need two C0s, and instead you can do it with a single C0 gate here. However, if you start to try and do this trick for different angles, you don't get that same benefit. So if instead I want to do a RZ of pi over 2, whether you're using optimization level equal to 0 or optimization level equal to 3, you're going to have to transpile that to 2 C0s when working in this basis of C0s. So this now is where I want to get to this idea of continuous gate sets. So continuous gate sets is now wanting to reveal how you can take that cross-resonance interaction and instead scale it to get these same implementations. So to do this, I just want to walk through the cross-resonance gate one more time, specifically pointing out these dimensions right here. So when these cross-resonant pulses are tuned up, there are calibration methods that I didn't jump into, but basically you're going to have some characteristic duration. When calibrating, what you'll do is try to make that duration as short as possible until you start to see those sort of leakage errors. And then from there, you start to do the calibration of your amplitude and phase and a variety of other things. Ultimately, what will dictate the rotation on your control qubit, or sorry, on your target qubit, will be effectively the area under the curve here, which is sort of dictated by this alpha star, where A star is the amplitude when for your initial calibration. This W is the sort of width of your Gaussian square pulse, and then you have these extra envelopes at the end here. Now, in order to actually create a continuous gates set, what you want to do is take the total area under here and scale it. So now this is actually something that sort of natively happens when you're calibrating your gates, in the sense that when calibrating your gates, you are going to take the duration of your pulse and you're going to sweep it, and you're going to take the amplitude of your pulse and you're going to sweep it. And by sweeping those two things, you actually are getting these partial rotations on your target qubit. So when calibrating, you're actually, in some sense, doing a continuous gate set. You have to sort of refine it in order to get the desired angles. But the goal of what I want to show here is how you can take the default backend properties and use those and scale the pulses in a clever manner such that you don't actually end up having to do any additional calibrations. So you're going to now have this alpha of theta, you're going to normalize by that angle of pi over 2 relative to the initial calibration point based on the target theta that you actually wish to achieve. Specifically, the way that we're going to scale this amplitude to start is we're going to take the width and scale it down. So the reason that we start with the width here is that the width of our pulse will generally, by scaling the duration of it, behave in a more linear fashion than scaling the amplitude. The amplitude can often be quite nonlinear, so that would end up requiring that we would potentially need to do some extra calibrations. And the goal here is to try and avoid that. So instead, we're going to take this width of theta and implement it in that way. So this is now how we can begin to scale down the pulse and get these partial rotations on our control qubit, or sorry, on our target qubit, without having to do any sort of calibrations. Once your width gets to 0, you then have two options. You can now try and scale the rise fall times of these pulses. We decide to avoid this though, because by doing so, this is where you then start to get into those issues of having undesired excitations outside of your computational space. So instead, what we're going to do is we're going to keep those rise fall times fixed, and instead, at this point, begin to scale the amplitude of that pulse in this sort of fashion here. And then this now is actually how you can achieve these partial rotations or these RZ of thetas only using a single C naught, or using the native basis, or sorry, using the backend calibrations as your starting point. So this is now great because you've basically built this continuous gate set that then allows you to do it instead of using those two C naughts. To actually see how does this perform, here we show a plot that sort of compares the two ways of going about it. So namely, the blue dots are using this double C naught version. So we're going to have two C naughts with those RZ rotations. And then we're going to implement it for varying angles here. And then we have this parametric version in which you have, we use this technique of scaling the pulses to get this sort of continuous gate set. Now, what I point out here is that the double C naught implementation has that virtual Z gate and two C naughts. So its error should actually be independent of the angle, which is basically what you see here, that the error ends up being sort of up to fluctuations independent of any sort of angle that you're trying to implement. Whereas the parametric version, or this continuous gate set version, instead what you're seeing here is that as you begin to go to smaller angles, you are going to have shorter widths. And then from that, the duration of this pulse will be shorter. And in this way, you actually end up improving the fidelity. Which is what you can see here, that as you get to smaller angles, this continuous gate set implementation will give a better result than if you did the double C naught version. And ultimately, as one might expect, they end up meeting when you have this angle of rotation of pi, say, because this is actually using the same total duration of two pulses. So this now is, say, potentially useful for something like a Pali feature map, is when you look at the gates from this here, you can see that this has a similar structure to that ZZ Pali feature map. What I want to do, though, is sort of elaborate on what one might be able to do as a continuation of this. Namely, I want to consider different sorts of gates. So earlier I mentioned this RZ gate, but you also have, say, a controlled Rx or a controlled Ry. When mapping that to the back end, again, you see these two C naughts with single qubit gates on, in this case, the target qubits. And now what I want to do is show how you can actually go from not only having that sort of CX of theta gates, but having it for arbitrary CX or doing it for all three of these gates here. I just want to point out this top one is, say, useful in QAOA-like circuits, as well as that Pali feature map that I just mentioned. But then you can say this controlled RY, say, is useful for portfolio optimization, where I reference a paper that sort of discusses the use of this controlled RY gate. So how is it that we sort of expand and allow ourselves to have these different gates that aren't just the controlled RZ, say? So to do this, here we talk about this CX gate where we've built this natural ZX interaction, and then we've talked about how we can scale that. What I want to point out is that if you now take the phase on your cross-resonance tone and you begin to sweep that, what you can actually do is turn yourself from being in a CX to being in a CY type gate. So then now you adjust the phase and then use those same scaling techniques, and then now you can end up implementing that, say, a controlled Y rotation. And then similarly, now you have the ability to get this CZ gate by applying Hadamard's onto your target qubit. So what this is basically saying is that your CZ gate is locally equivalent to a CX gate in the sense that you apply Hadamard's on your target, and then in this way now you can take a CX gate and turn it into a CZ. And so through the variety of these tricks here, you can now have a continuous gate set for CX, for CY, and CZ. What I think is exciting about this is now you can use this trick as a way to implement arbitrary SU4 gates using this continuous gate set. So namely, we're going to use this idea of a CAC decomposition, where what I want to do is I want to take an arbitrary unitary and map it to different basis gate sets. So when I map it to the standard C0 basis gate set, this is what you see here, where you have C0s with single qubit gates that exist. Whereas when you do the continuous basis gate set version, where you have this RXX, RYY, or RZZ, then you can end up having these pulses be the thing that you use to map instead. Now, what's nice about this is that if you use these, as long as these alpha, beta, and gamma end up being smaller angles from that then as I mentioned earlier, that ends up causing this, or allows this implementation here to have a shorter duration than the C0 version. When we look at the SU4 results here, so that same plot of the QPT fidelity that I showed earlier for the CX, but if instead we do it for an arbitrary SU4 where we pick different angles, you can see that if as the relative duration of your SU4 is decreased, you're also going to get a general improvement in your gates here. I bring this up to mention that if you use this CAC decomposition, you can actually sort of map this swap of theta in which you have the C0, RZ, C0 followed by a swap gate into this basis set as well. And then by doing so, you can actually now, say, improve this as well. And so maybe if you have some sort of Pali feature map followed by a swap gate, using this CAC decomposition with these three different points might help give some slight improvements in whatever results you're using. So this is the conclusion of this lecture. At this point now, I want to sort of point to the lab that we have, Lab 5. In this, we're going to explicitly try and develop this Pali feature map, which you may have done at many points at this time. We're going to do the simulation of these QPT circuits with and without noise. And from that, I hope to reveal the impacts of the readout errors. So quantum process tomography is quite sensitive to sort of spam errors that you can have. So because of this, it's in order to get good results when doing QPT, you really need to make sure that you implement that error mitigation technique that I spoke about in the previous lecture. And then out of the sake of sort of convenience, we weren't able to do the explicit pulse study of this. So instead, what we do is in our noise models, we do a sort of analogous study of the quantum process tomography improvements through that scaling technique, but by just adjusting the characteristic duration of a CX gate in your noise model, say. So it's not equivalent to what's actually happening on the underlying hardware, but hopefully it reveals the sense of how this all works. I hope that this was useful and that you had a good time. Thank you for listening, and I will be available for any questions that you may have. Thank you.